everybody to our SIG webinar. For those of you who do not recognize Ian's name, that's probably because you have not interfaced with the codes Burnman and Aspect. Ian is one of our CIG developers and one of our, we welcome to our family of CIG PhDs. He has recently finished his doctorate at UC Berkeley and has been fortunate enough to pursue both of his passions in software development and computational geophysics and geodynamics by working at UC Berkeley on the Jupyter project. So with no other further ado, Ian.
All right, thank you for that introduction. Just as a side note, I can't see the chat window at the moment, so if there is something that comes in, I'm happy to take questions at any moment, but somebody will need to ping me if that happens.
Yes, I will be happy to help you with that.
Great, thanks, Lorraine. So I'm here to give a brief introduction to Project Jupyter and how it can be used for the geosciences specifically. I'm going to give a sort of historical and technical overview of what the project is, and then hopefully I will be able to show you some usage of the notebook, some cool applications of it in the field of geosciences, and then I'll briefly touch on some more advanced usages just to give you a flavor of what types of things can be done with it. So to start with, I'm going to go over what the Jupyter project is. I imagine that a lot of people, though probably not everybody, have seen these Jupyter notebooks, which were formerly known as IPython notebooks. But just to get everybody on the same page, Project Jupyter is a collection of tools for doing interactive and exploratory data analysis, and it includes tools for both doing that data analysis and then subsequently sharing and publishing that data analysis. So that's a sort of very high-level description. It's probably pretty vague, so I'm going to go a little bit into the history of how this project came about. It started in 2001 under the name IPython. It was created by Fernando Perez, who was then a graduate student at Boulder, and I guess he was trying to do some procrastination on his thesis and wrote what is essentially a fancy REPL for Python, where REPL stands for read, eval, print, loop. The idea being many dynamic programming languages they'll give you a prompt and you type in a command to that prompt and then you see the output of that command. That's very text-based and doesn't really provide a lot of feedback. So the initial versions of IPython just sort of added some nice features tacked onto a normal read, eval, print loop. So you have things like syntax highlighting. You have things like you can maybe bring in some documentation. If you could maybe have some tab completion. Just things that make working in a dynamic computing environment a little bit nicer. So I've got up here a screenshot of the current iteration of the IPython console, though in sort of morally, it hasn't changed a whole lot since then. Over the years, it became clear that this project, IPython, was developing tools that were useful for other programming languages than just Python. You know, many of us in the geosciences are most familiar with Python, but there's also a lot of people who use R. Increasingly, there's more and more people who use Julia. And it became clear that these tools were useful for other programming languages besides that. And so as this started to come about, it became clear that the IPython name was less and less appropriate. So a few years ago, I don't remember exactly what year, something like 2013, 2014, there was a large abstracting and rebranding effort where the team went and pulled out all of the Python-specific stuff from this project and had that be a separate IPython, have all the Python-specific stuff be IPython, so that still exists. But then all the stuff that's language agnostic got rebranded as Project Jupyter. And so the idea is that people in different programming language communities can write what's called a kernel, which is just an interface to that language's interpreter. They can write what's called a kernel and then plug that kernel into the Project Jupyter front end. And so you can have, these readable print loops. You can have what we'll see in a moment as the notebook interface. And all of these things are front ends which can plug into different programming languages, whatever suits your needs. To date, there are over 70 of them. I've thrown up some logos here of some of the most commonly used ones. We've got the IR kernel, the iJulia kernel, and then the classic IPython kernel. This is a chart of the different components to this project. You can see that it's really a very complicated project with a lot of different repositories that hold different aspects of the code. I don't want to get too lost in the weeds here, so I will just try to note. Is my cursor showing up?
Yes.
Right now? Yes. So I'll just note that these ones in green here are the front ends to the Jupyter project, and they're the things that you interact with on a day-to-day basis. And you may be able to tell that the notebook front end has the most arrows pointing both into it and out of it. This is sort of what has become the flagship product of Project Jupyter, rather. So to come back to this this console interface, this is a pretty limited interface. It provides some nice things like it's got syntax highlighting, it's got automatic indentation. You can show tooltips and documentation in line. Maybe you can do some light formatting, but at the end of the day, it's still pretty much text-based, and it does not give us the rich programming environment that we would be more interested in. And so the decision was made in about 2011 to bring in the web browser as an alternative front end to these computational kernels. The idea here is that we would like to be able to bring in richer rendering and outputting capabilities to these computational kernels. We want to be able to show images, we want to be able to show video and sound and formatted text. That's a lot of stuff to have to render, and to write our own piece of graphical user interface software that is able to render all those things is an enormous undertaking. It's way bigger than what is still, to a large extent, an academic project. It's a way bigger problem than an academic project can tackle, especially to do it in a cross-platform manner, so that people on Windows, Linux, and Macs can all look at the same documents and run the same documents. So the decision was made that, well, web browsers already take care of a lot of that stuff for you. They can format text nicely. CSS is maybe not the best styling language, but at least it can do that. It can display images. It can display equations through math jacks. It can do sound and video, as anybody who's watched Netflix recently can attest. And it can also have UI elements like sliders and buttons and such. And so the idea is if we can hook in the Jupyter kernel machinery into a modern web browser, we basically get all that rendering stuff for free and don't have to support it. So the overall architecture of what has become known as the Jupyter Notebook is we have this user who sits in front of a web browser. That web browser is hooked up to a server. This server is basically the connection between your Python or whatever you like kernel and the web browser. And so this handles communications between those two things. And then there's also a file on disk, which you're loading to and saving from at regular intervals. So in case you haven't seen these things before, this is a very high-profile example of a Jupyter notebook that came out last year. This came out of the LIGO project, which is one of the largest, if not the largest, NSF-funded projects of the last couple decades. and this is what famously detected the existence of gravitational waves last year. And one of the really neat things about it is that when they made this announcement, they also published a series of IPython Jupyter notebooks, which take in the raw data, process it, and essentially show the existence of gravitational waves. And they made this publicly available, so you could download it, rerun the data analysis, and sort of convince yourself, if you were so inclined, that gravitational waves actually exist. One of the things that was really neat about it was this came, I think, a little later. I think Minrig and Kelly actually added this aspect to these notebooks. But what he did was he took the frequency data of the waves and actually made some sound files from it in the notebook, and then was able to embed that as an output so that you could actually click play and listen to the sound of the universe, as people have poetically called it, all in the same analysis. So with that sort of brief introduction, I'm just going to talk more concretely about what a notebook is. And central to the concept of a notebook is the idea of cells, where a cell is just a unit of text. That text can either be code or it can be markdown, and those are the essential units of the notebook. And then you will run cells one at a time. There are two main flavors of cells. The first of which is a code cell. That's where you put code, as the name suggests. And the second of which is a markdown cell. Markdown, if you haven't run into it, is a lightweight markup format similar to HTML, and it frequently compiles to HTML, but is easier for humans to write quickly. And then when you have a code cell or a markdown cell, they will then output something typically. And in the notebook, it's basically anything that HTML can handle is something that is a valid thing for your cell to output. So here is an example of a code cell. You can see that it's got syntax highlighting, it's got commenting. This is a Python cell. So this is the Hello World program for Python. And this is a cell that I can actually execute. And so what I've done is selected that cell and hit Shift-Enter, and that's executed the cell. And you can see the output of it is Hello World. Yes.
And we have some people joining us by Hangouts, so we lost the screen share. So if you could just repeat that last slide and make sure we're sharing screens again.
Sure.
We can get to the end.
Let's take a look at the screen share.
There we go.
Are we up and running again?
Yes, we are.
Okay. Okay. Can people see?
Yes. Hello World.
Awesome. So we can execute this cell, and we get the output of that, which is Hello World. This is not a very interesting program, but we can start doing some math. Say 2 plus 2, we get 4. Let's see. I don't want to get too fancy because live coding always goes terribly, but let's say we can make a quick plot, and we'll see how well my live coding abilities are. And so you can see that I've made a plot of sine of x, and it's output to the screen. And so you may have noticed that this is a live presentation. I'm actually running a Jupyter notebook at the moment as a presentation. And so all these slides are live. So that's an example of a code cell. This is an example of a markdown cell. So you can see it's got a header. I've got a list, and the list items have some important equations for geodynamics in them. The eagle-eyed among us may notice that I have put an error in the Navier-Stokes equation. This minus sign is incorrect. So what I'm going to do is double-click on the cell. Now we see it in the unrendered format. So you can see it's the same thing, and I've got LaTeX equations, here and here. And what I'm going to do is find the place where there's the incorrect sign, fix it, and then press Shift-Enter, and we've got a corrected Markdown cell. So these are, all very well and good, but each of these two slides, this one and this one, by themselves are maybe not particularly interesting. This is essentially, just running some code and looking at the output of it, and this is essentially, writing something in an impoverished type LaTeX form. So where this really shines is the fact that you can have your text and your code interleaved and together at all times. And if I were to editorialize a little bit, I would argue that the closer that your text and your prose lives to your code, the less opportunity there is for error. I can't say how often in my life, you wind up with some text, and in the text are some numbers, and those numbers are the result of some calculations, and you can't really remember exactly with which version of the code you ran those calculations to get that number, and it's really easy for your manuscripts and your figures to get out of sync. There are all sorts of synchronization problems and versioning problems when you have your manuscripts and your code being separate from each other. And so this is a place where I think the notebook really shines, is that you can have code, you can have prose, you can have equations, and you have the output of that code all in the same place. And so you can have a lot more confidence that what you're showing and what results you're describing in this is accurate and correctly reflects the code that you've written. So this is what I'm showing here in this image is a screen capture of a notebook that was made by Nicholas Swanson-Heisel and colleagues. He's a paleomagnetician at UC Berkeley in the Earth and Planetary Science Department. And for every manuscript that he writes, for every paper that he publishes, he has companion IPython notebooks, Jupyter notebooks, which have all the code and some explanatory text for every figure that he generates in the manuscript. And so this is a really nice way to be really confident that the results in your manuscript are accurately reflecting the work that you've done. Furthermore, it makes it complete if you make these things public, and these things are, and if you put it up on GitHub, it is public. But if you make these things public, that's very easy for your colleagues to then, look at what you've done. And as somebody who is interested in transparency in science, I think this is a really powerful tool for that. So with that introduction to what a notebook is, I'm just going to really briefly show a couple cool things that you can do that are more earth science oriented. This is a package called Carpi, which does mapping. It has a lot of overlapping capabilities with GMT, which I know a lot of people still use. I find it a little bit easier to read. So what this block of code does is makes a map and plots a great circle between San Francisco and London. And so if you were to do that flight, this is more or less the path you would take. Let's say that I'm not interested in going to London anymore, and instead I want to go to Johannesburg. We can update this code. I initially had the full name Johannesburg, and I felt that I couldn't do it without typos. And so if we update the places where it had said London, if all goes well, and even with that, I can't manage to spell it right. It should update the plot and show a great circle to between San Francisco and Johannesburg. And there we go. Great. So this is a nice way of generating static maps. But one of the nice things about having a notebook is that you can also have dynamic maps. The web browser is a very dynamic environment. So this is something which has a plugin for Leaflet, which is a dynamic map plugin for the web. And what I've done, what this block of code does, is it loads in a feature set of all the borders of all the countries in Europe and plots it, and I can pan around and highlight different countries, and you can have it perform various actions upon hovering over. So these are really very dynamic documents. And I don't want to really get into any one library for it, except to say that there are a lot of really high-quality libraries out there that interface well with Jupyter notebooks and can give you really rich output capabilities. So I wanted to sort of take the last. Are there any questions about this at this point? I again can't see the chat, but I'll pause here in case anybody wants to ask questions about what they've seen or what they're looking at.
I don't see any questions or any typing right now.
Okay. So for the last portion of this talk, I wanted to talk about some more advanced usage of the notebooks. These are things that you can do. The fact that it exists in a web browser allows for some really neat tricks that wouldn't really have existed in the old days of just having a readable print loop. So we haven't really seen much of it yet. I guess that leaflet example was a bit of an example, but you can have interactive user interface elements. You know, web browsers have access to sliders and buttons and stuff, and you can actually hook those into your code and start having a more interactive document. And because these exist in a web browser, it means you can actually serve them over a network. And what I mean by that is that the place where the code is running doesn't have to be the same computer that you're viewing it on. Currently, this slideshow that I'm currently running right now is running locally on this computer, so all the calculations that I've been showing are running locally on this computer. But they needn't be local to this computer. They can actually be served over the internet. And so hopefully this is a demo that will work, and this is something which was largely set up by Timo Heister, who I think I saw in the participants list. But this is a link to a web server that Timo has set up, and this link will spawn a temporary notebook server when I go to it that will give me some options of different notebooks to run, and I will be able to interact with them on his server in South Carolina. So I've clicked on this link, and hopefully, okay. So I've successfully logged in. So to recap what we're seeing here, I'm sitting here. So that this notebook server is running on a server in South Carolina. I've logged into it from a laptop in Oakland, California. That is being rerouted by Google Hangouts to Lorraine's computer in Davis, which is then being screen shared to all of you through Adobe Connect. So we live in the future, I guess, is the point. That was a list of available notebooks. So by clicking on them, I can now see different notebooks that are available on this system. So this is an example notebook for a project that I've been involved with, and Timo is also involved with, called BERMAN, which is a library for calculating thermodynamic and thermoelastic properties of minerals in Earth's mantle and other planetary mantles. And I can run the various code cells. And what we're doing here is we're going to load in we're going to create a mineralogical model for the mantle and compare the wave speeds and densities with that of Prem. And so, again, that's not the focus of this talk, so I won't be going into what these do. But what we're doing, I'm dynamically running these codes and coming up with these plots. And there's more to it there. So that's a nice sort of introductory example. But what is a more interesting one is one that we've been cooking up, that we've been playing with recently, which is a more interactive demo. So this is the idea here is to create a notebook that has that's a bit more user-facing and is a little bit less code-oriented. So this is more of a notebook as a service type situation. So this is the same type of notebook we were looking at earlier, except for we've just hidden the code cells. But what we've made here is, again, we're going to try to match the shear wave speed and the density of Prem by coming up with a mineralogical model for the mantle. And we're going to have one lever on this mineralogical model of the mantle, which is the amount of perovskite in the mantle. And so this here is a plot of the shear wave speed, where the blue line is the computation, and the red line is what Prem has for that, and then this plot is the same thing, but for density. And so you can see we're not doing a very good, we're doing maybe an okay job of matching Prem for the shear wave speed, but a really bad job for the density. And the reason we're doing a really bad job for the density is actually probably because this model doesn't have much iron in it. And by much, I mean it has no iron in it. But what we've done for this notebook is we've put in a slider here. And this slider, I can click and drag. And when I drag it, it dynamically updates the plot as a function of the amount of perovskite. So you can see that as I increase the perovskite amount, the density gets a little better, but the shear wave speed gets a little worse. And I can swing it back. So this is an example of a sort of a more advanced thing you can do with the notebook, where you can have it more as a service than as a code notebook. It's got interactive widgets, and it's serving it over a network, which means that anybody could log into this. In fact, I encourage people who are watching right now, you can log into this server, or at least 6 of you can log into this server, and do the exact same thing that I'm doing right now. You don't need to have installed anything. You don't even need to have a Python install on your machine, and you will be able to run the same code that I'm running right now. Any questions about what I'm doing here? You're going to have to take my word for it that this is something that is currently 3,000 miles away from me. This where this code is being run. Okay. Where did my slides go? There's my slides. Okay. So another notebook server was brought to my attention earlier this week, thanks to Heiner Ego. They have set up a really impressive set of, if you go to seismolive.org, they've set up a really impressive set of notebooks which are running using the same technology that I just showed you, only this notebook server exists in some supercomputing center in Munich, I think. And so when I've logged into this, they've got a whole lot of examples set up. There's really well done. I'm just going to open one example. So this is a notebook that is running in Germany at the moment, but I'm interacting with it, and we can run the cells. I'm pressing Shift-Enter again to run them. And as they run, we're generating these, to my eye, very attractive plots showing, of estimating, let's see, correlation coefficients and phase velocities using the seismological software OBSPy, which I've not used much myself, but appears to be a very well done set, a very well done piece of software. Yeah, so I think those are pretty neat. The final thing I wanted to talk about, just very briefly, both of those examples we just looked at, they both spawned temporary notebook servers so that you could interact with these example notebooks for a limited amount of time, but they're not really set up to do any kind of persistent notebooks. So if you want to have a more long-lived project, something that lasts longer than a demo, you'd want something that's persistent so that you can actually save your work and come back to it later. And so to that end, there's an additional, there's a sort of meta project on top of Jupyter Notebooks called Jupyter Hub, which provides the infrastructure for actually setting up these notebook servers and having different people be able to log in and get persistent notebooks so that they can save things, they can collaborate with people so that multiple people can edit the same notebooks. And this project has been used with some really astonishing success in teaching, where currently at UC Berkeley there is a data science course which has, I think, verging on 1,000 students in it at the moment, and none of them actually need to have a development development setup installed on their system. They all are able to just log into a central server, which they've got a beefy enough set of servers that they can accommodate 1,000 students. So they log into the server and they get live notebooks, which allows them to collaborate on projects, allows them to do homework assignments, and then submit those homework assignments, all with only needing a web browser installed on their system. So it can be a pretty impressive and powerful tool for teaching if you have the infrastructure to actually serve these notebooks to students.
So Brad has a question for you, Ian.
Yeah.
Brad wanted to know how well Jupyter is suited for large 3D visualizations, for example, things that are normally done with ParaView or Visit. Can you bring that in?
Large-scale visualization? Or like visualization
large 3D.
I don't know that, so I know that both ParaView and Visit have some limited Python scripting ability, but I'm not aware of any plugins that they have for notebooks. There's another project called YT, which is primarily aimed at the astrophysics community that does have good integration with Jupyter, and that is, it it may be possible to put geophysical data sets in that as well. So that there's also another project made by Enthought called Maya V, which has some 3D interactive capabilities, which I think can integrate with notebooks. So I think there are some options, but I'm not aware. If somebody feel free to correct me, but I'm not aware of peer review and being able to do it.
Thank you.
But that was a good timing for a question, because that's the end of what I've got. Thanks everybody for listening. I'm happy to take any questions, or you can direct questions to me at any of these places offline.
Yeah, so we have some people typing in questions.
Yeah,
but while they're doing that, can you maybe take us out to the Jupyter website and show us how to find resources on Jupyter,
yeah.
You know, for good tutorials, and maybe how to find other
absolutely.
libraries that we can use with notebooks?
Absolutely. So this is another thing I could mention. If anybody, this is the Jupyter website, but if anybody has any, there's a conference that's coming up, the very first JupyterCon in August in New York City. If anybody has cool stuff they want to show and talk about there, abstracts for this conference are due, I think, in 3 or 4 weeks. So consider that. But this is just the main web page. There's if you want more documentation, I would say just choose the documentation tab. We put a lot of work into documentation, and so but it's the link to it would be right here. And then the GitHub, the issues pages for individual subprojects are very active on GitHub. So that would be a good place if you have specific questions.
Is there a good resource to find the libraries that are associated with the notebook, or is it just embedded here in the documentation?
So that you can find at the top level Jupyter organization on GitHub. So I just opened that up. So as long as I'm still screen sharing, people should see this. There's a lot of different repos. Unfortunately, I would say there's confusingly many repositories, so it can be a little tricky to find the one that's most relevant for specific questions you might have. Though I would imagine a lot of the time that's going to be Notebook is what.
So nobody has curated these yet. Then is what you're saying. They're all just kind of separate projects within the GitHub.
Yes. They're each separate repositories within GitHub.
Okay, so we have another question. Are Jupyter files readable by humans? Is there a danger of people investing in converting to Jupyter notebooks and not being able to easily regenerate the information in other tools if Jupyter is no longer maintained?
Yeah, really good question. So the answer is a qualified yes. The format that they're stored in is JSON, which stands for JavaScript Object Notation. It's really a lightweight serialization format that's really common in web development, and those are human readable, though you wouldn't want to make a habit of it. So if Project Jupyter died and all the code disappeared from the world overnight, but you still had your notebooks, it'd be a pain, but you could open it up with a regular text editor and pull out all your code and all of your prose. It would all still be there, and it would be human readable, but not an enjoyable reading experience. And that being said, there is also a lot of effort put into backwards compatibility. So the front ends for the project are rapidly moving. We're adding a lot of stuff all the time, but the actual format itself is, we try to be more conservative with it.
So the back end you say is JSON, so we can actually use this also as a JSON viewer?
You could absolutely use a JSON viewer to read them, and that would be completely human readable.
Okay. Is there a smart way to link parallel computing from Jupyter?
People have been using notebooks as a front end for submitting jobs on large compute clusters. I know that the people who are developing Underworld have done some cool work trying to send off jobs to clusters using notebooks. I haven't done it a lot myself, but it is possible. And I know that some of the national labs and supercomputing centers in the U.S. are exploring doing similar things as an alternative to like batch systems.
So that would be Exceed is looking at this, for example?
I'm not sure if Exceed is looking at it at the moment, but I know that NERSC is looking at it, and I know that the Minnesota Computing Center is looking at it. Minnesota Supercomputing Center.
Yeah. There's a lot of new technology coming down the pipeline. Everybody can do everything. Okay, and are there any more questions? While we're waiting for those, I want to thank Ian once again for giving us a good introduction and showing us some good examples of how to use Python and, how to use Jupyter notebooks in our research. The LIGO project is rather inspirational of how we can publish our research and have many eyes to look at it, as well as some of the fun stuff you guys are doing with BurnMan. Our next month's webinar will be switching gears a little bit. We'll have a speaker who will be talking about the spectral element method and some of the new things that are coming along, development for that in relationship to the seismology code SpecSim. So if we have no other questions, thank you everybody for joining us, and thank you everybody for your patience while we get the technology working.
Thanks, everybody.
Everybody's saying thank you. Toby says